G'day chemistry students. In this video, we're going to be looking at what conjugate acids and bases are, as well as these new things called amphiprotic substances. Let's get into it. So first off, I want to talk about this idea of conjugate acid-base pairs. We already know that with our general equation, we have Ha, which is hydrogen and the anion being the acid, and B being the base. We're forming Hb plus and A minus. In other words, the acid donates its hydrogen onto B, the base, which is accepting the hydrogen, forming Hb plus, and leaving the acid as A minus. However, with acid-base interactions, we're actually forming an equilibrium where this neutralization process happening in the forwards direction can also happen in the reverse. As a result, the acid that's here, Ha, ends up forming something that acts as a base when it goes in the reverse direction. So Ha here is an acid forming A minus. But if we go in the reverse direction, A minus, the anion, is the proton acceptor because Hb will act as the acid donating it back. So this here would be the base, and this would be the acid in the reverse process. So here I have a pair where I've got the anion being combined with the hydrogen, acting as an acid, and then the anion accepting a proton, acting as a base. We call this a conjugate pair. This is the acid and its conjugate base. Conjugate meaning sort of like on the other side. It's the pair that it works with. Conjugate referring to the fact that it will not be an acid, but be a base instead. We then have B over here, which is the base. It accepts a proton to form Hb plus. However, when we work in the reverse direction, it acts as an acid, donating its proton and reforming into B. So again, we have another conjugate pair, the base and its conjugate acid. Looking at an actual example here, we have hydrochloric acid donating its proton. Its conjugate base is Cl minus because in the reverse direction, it will end up picking up or accepting a proton to reform into HCl or hydrogen chloride. The water is acting as a base in this reaction because it's accepting that hydrogen from the hydrogen chloride and forming hydronium. The hydronium acts as an acid because it can donate its proton back to the chlorine and reforms into water. So we have our base and the conjugate acid. Another example here, this is one that doesn't involve water. We have sulfuric acid donating a proton to the ammonia and forming hydrogen sulfate, which is the conjugate base, and the ammonia accepting the proton, forming the conjugate acid ammonium. Now, ammonium will donate a hydrogen back to the hydrogen sulfate, reforming into sulfuric acid. We can find a bunch of different conjugate acid and base pairs. They can come up in all sorts of charts and all sorts of things. So for example, we have our acid on this side and the base on the other. So we have hydrogen chloride and its conjugate base, chlorine ion. We could also say that chlorine ion is a base and that its conjugate acid would be hydrogen chloride. They can sort of act interchangeably. Last thing that I want to talk about in this video is the concept of amphiprotic and amphoteric substances. Now, an amphoteric substance is something that can be both an acid and a base. We've already said that water can act as an acid and it can act as a base. That means that it's amphoteric. However, there's a little bit more of a specific definition and a word that we're going to be using a lot more than amphoteric, which is amphiprotic. So if something is amphiprotic, it means that it is in particular both a Bronsted-Lowry acid and base. It can donate a proton, and that's where the protic part comes from, and it can accept a proton like a base. So they both act as an acid and a base under that Bronsted-Lowry definition. So we know that water is amphoteric and amphiprotic. So it can act as an acid and donate a hydrogen, forming hydroxide. It can also accept a hydrogen, forming hydronium. However, not all substances are amphiprotic, even if they're amphoteric. So for zinc hydroxide, not only can it act as a base like we would expect it to, but it can also do some very special chemical interactions where it acts like an acid. Something like this here, this amphoteric but not amphiprotic substance is not really a large part of this course, but is something certainly to acknowledge, especially when you see a term like amphoteric. In the scope of this course, we can generally consider that amphoteric and amphiprotic mean roughly the same thing, because things that are amphiprotic are essentially always amphoteric. Thank you very much, everyone. In the next video, we're going to be looking at pH in a lot more detail, defining what it is, and starting to talk about how we can use it mathematically. But until then, have a good one.